me? Yeah. So my name is Gerrick Lindberg, and I'm taking today's lecture about atoms and molecules. And so it's front-loaded with the dense stuff, unfortunately, today, but I'm going to tell you about atoms, and we're going to build up from there to molecules and try to understand why molecules form, what is bonding, and so on. And then we have a few labs or experiments to do at the end. So, first of all, I just wanted to start it out with kind of what I hope you guys learn from this lecture, so you can kind of pay attention to what I think are really the important questions that come out of this. So I think obviously the most important, or the first thing you want to know is what is an atom? What's in an atom? What causes them to look the way they look, and so on. And then we want to know, why do individual atoms come together? Why do they form bonds? And then why do they form molecules with those bonds? And then on top of that, we want to know, just from this kind of simple understanding of simple forms of bonds, what do we know about the molecular properties of those substances? And so we're going to stay, I think, hopefully pretty simple throughout all of this. But hopefully from this simple level of information, you can learn quite a bit about atoms and then molecules and the kind of properties that arise out of that. Okay, so obviously these are not new subjects. People have wondered what is around them for quite a while, why it behaves the way it does, what exactly is going on. And so there are two Greek philosophers. Interestingly, the one that came first, Democritus, had this idea that matter is discrete. And so if you keep breaking substances or matter into smaller and smaller pieces, eventually you get down to some building block that is inseparable, or at least inseparable in terms of maintaining the properties of the larger substance. And I was trying to look for how you would come up with this idea, and I didn't really get any good answers, and obviously I'm not going to go back and read the original Greek to figure out what was going on, but I found a little bit about, I guess he was very into sculpture, and I think he himself did some sculpting, and I guess this came about from him, chiseling and getting a piece of break off of granite and then chiseling more and like continually breaking this thing down, and somehow either he was inspired or for some reason he just had this idea that at some point it's got to stop. Maybe it's driving him insane, I'm not sure. But he had, from this kind of story to justify where he came up with this idea, he chisels and chisels and just has this idea that at some point it has to end. And so this is kind of, I think, at least in Western society, the first documented case of this. I was talking to a lab mate of mine who was saying that this is actually late, that if you go to Indian texts, I guess they predate this by 3,000 years or something, the idea of this discrete small matter that captures the same properties. I didn't know as much about that, so I didn't include that. The other interesting thing about Democritus is apparently he's the laughing philosopher. So all of the pictures, or all of the busts and so on of him, he has this crazy kind of look to him, like it looks like he's about to eat something, and I guess he's supposed to be laughing. Okay, and then following Democritus is Aristotle. And if you take any courses kind of in the history of Western science, Aristotle looms over them as this guy who did an unbelievable amount of work back during the height of the Greek civilization, and a surprising amount of it is wrong. And so he had this idea that matter is continuous, and for some reason this idea came to dominate the thinking at that time, and it persisted throughout the Middle Ages. And so I'm not going to talk really about the debate between these things, but I think you can look at these two ideas, and if you reject that we know the truth, or you set that aside, it's kind of hard to understand how you would choose between these two ideas. And I think it's kind of an interesting kind of philosophical debate in the way that science is developed and so on. But nonetheless, there's a long history of trying to figure out these problems. So once we come to be more to the more modern era, we have more sophisticated techniques, and we have people coming up with all kinds of information, discovering some subatomic particles, and so on. And John Dalton was able to kind of state the first kind of modern version of the atomic theory of matter. And so he, at this point, it was known that certain substances have kind of innate properties to them, and those things can be called elements, so like hydrogen, helium, and so on. And he came up with the idea that elements are composed of individual atoms, and those atoms carry all of that same information as the elements. So an element would be like a group of atoms. And then atoms are indestructible by normal means. So as we go through all of these kind of, you know, chemical reactions and so on, kind of normal everyday life going on around us, atoms are there and they're being moved around, reactions are occurring, bonds are happening, but the atoms themselves are staying the same. And so, just restating that same thing, they have these properties that are innate to the individual atoms, and so as we go through reactions, molecules will express different properties, but those fundamental building blocks, the atoms, remain pretty much unchanged. And again, these things can form bonds, and interesting things can happen on top of that. Okay, so what are the building blocks of an atom? So what are the important things that you guys think that me as a chemist are going to consider for an atom? So go ahead.
The nucleus and
the
electrons.
Nucleus, what's the nucleus composed of?
Protons and neutrons.
Exactly. So the first part is atoms are composed of protons, neutrons, and then electrons. These things are going to behave in some interesting way, interact in some interesting way with each other to give rise to everything that we're going to talk about from here. And so what do you think are the important characteristics of these particles that we're going to want to consider as we talk about what makes up an atom, what causes an atom to be an atom? Yeah, definitely. Some of these particles are charged, and so the charge is going to be very important. What else?
The numbers of.
Yeah.
Bond.
Yeah, we're going to talk about that a little later. Yeah, definitely.
What did she say?
How
they bond. So what do you think would be, there's one other one in particular that is very important for the reason they behave the way they do.
A part of the atom, you mean?
Yeah, these subatomic particles. So protons and neutrons are in the nucleus, right? There's this very dense portion in the nucleus. And then electrons are this diffuse cloud around it. So what do you think is a key defining distinction between...
Sorry to cut you off. They're attracted to each other or bound to each other? Is that what you're getting?
That would be part of the electrostatic force. What I'm actually getting at here is the mass difference. So electrons are essentially weightless when you compare them to protons and neutrons. And it's a very important distinction for the reason why these different particles behave differently. And so, and then size is another part of that as well. But I think two important ones that you guys picked up on are mass and charge. So the electrostatic force is going to be an important part of how these electrons arrange around the other particles. And then the mass is an important part for how we define atoms and understand what's going on. So these things were picked apart at the late 19th century, early 20th century. Various people did various experiments, and you can see the proton and neutron are very similar in mass, but the relative mass of the electron is about 2,000 times smaller. And so these are atomic mass units, so these are tiny values that we're talking about. But nonetheless, this electron is much, much lighter than the protons, and this is going to be important. And then we had someone point out the charges on these things are also important. So electron has a -1 charge, the proton has a +1 charge, so these things are going to attract each other just like playing with magnets. These two charges are going to give rise to important interactions between these particles. And then a neutron has no charge, so it's apparently along for the ride in terms of electrostatic forces. So how do these things actually fit together? What does an atom actually look like? So here are three models that I was able to find. I think these two you've probably seen before, and then this is an older one that was in the chemistry textbook that I was using as a reference. So we have these various pictures of what of an atom could look like. And so do you guys have any reason for rejecting any of these, or do any of these seem right to you guys? What do you think? Go ahead.
The Bohr model is no longer the accepted model because the electrons have their sort of I want to say fields or their space.
Yes.
Their orbits, or whatever you want to call it.
Yeah. So the Bohr model treats electrons as discrete particles,
Yes.
which we know is not true.
They're in clouds.
Yeah. So then the cloud model, where this electron, if we think of this as maybe a 1p orbital with one electron in it, it would be smeared over this whole space. And then we have this other one, which is definitely a straw man. We're going to reject it right out. But somebody had this idea that we kind of have matter as this kind of goo, where positive charge is spread somewhat evenly throughout, and then you have electronic charge also spread through it. And yeah, so we're going to reject this one. This one, it looks like it could be right? Like it has the same nucleus, it has electrons moving around that nucleus, but the fact that it treats electrons as discrete particles is incorrect. And so I think a lot of people fall into this The Big Bang Theory, the TV show, still uses this. It's pervasive through kind of the way we look at atoms, but this is not the most useful way to actually think about how electrons move in atoms or molecules. We want to think of them in terms of the cloud model.
With that cloud model, does it still say they're moving, or is it just everywhere at once, kind of?
It's everywhere at once, yeah. So it has an equal probability of, so these usually represent like a 95% probability, and it would be smeared across that. It would occupy all of those places. And so this is getting into a little bit more quantum mechanics than I want to talk about in this, and I think you guys would want to talk about with middle school.
I withdraw the question.
No, don't, I wouldn't withdraw it, I wouldn't avoid it.
No.
But the ideas of electrons moving are very difficult to talk about,
right,
particularly when you don't, you know, you're used to talking classical mechanics.
But in the school's books, they talk about them. In the science books, they do talk about electrons moving, unfortunately.
Unfortunately, and in some cases it might not necessarily be incorrect.
For grade school, I mean, they're talking about
Yeah.
It's more like occupying space.
Right.
I think that the materials we're using just like occupying space, but with a chance of being there. The thing is that the Bohr model is so complicated.